Welcome to Review Lecture 5.4, RC Circuit. Upon completing this, you'll be able to analyze the time-dependent behavior of RC circuits, determine the time constant of RC circuit, determine the charge and potential current in both a discharging or charging RC circuit at any time. Now, this is for Physics 222 students, that is calculus-based physics. If you are not a calculus-based physics student, in other words, if you're a Physics 122 student, please skip ahead to slide number 6, which is this slide. If you are a Physics 222 student, calculus-based student, then this is where you want to be, which is slide number 2. A circuit such as this with resistors and capacitors is called an RC circuit. It just stands for resistance and capacitance. If we wish to determine how the current through the resistor will vary as a function of time after the switch is closed, shown as the charged capacitor, it's initially charged, a switch, and a resistor. The switch is open, and the initial capacitor has an initial charge of Q naught. The initial capacitor voltage is V naught, which equals Q naught over C. Now, I drop off the delta because, frankly, nobody else does deltas on things. So I leave them off. Okay, just remember it's a potential difference across the capacitor, but it's good enough. Okay, the initial voltage on R, and I'm dropping the delta off of that too, equals VR. That equals 0. There is no current flowing, so I naught equals 0. Until at time t equals 0, you close the switch and the capacitor begins to discharge to the resistor. Now, the capacitor acts like a battery with a decreasing potential. Now, this is at a time t after the switch is closed, and now the current has been established and is flowing through the circuit. Kirchhoff's loop rule applied to this circuit clockwise is VC plus VR equals Q over C minus IR, which equals 0. Q and I are the instantaneous values of the capacitor charge and the resistor current. The resistor current is the rate at which the charge is removed from the capacitor, so I equals minus dq dt. Now, knowing this, the loop law for a simple closed RC circuit then is dq dt plus q over RC equals 0. Now, you can either integrate this or recognize it if you've had differential equation. This is a first-order linear differential equation. Either way will work. Q equals q naught times the exponent minus t over tau, where the time constant tau is defined as tau equals RC. So the time constant is the resistance times the capacitance. Now, there's some notes on units with this. 1 second equals 1 farad ohm. Whenever you have an exponent, you must make sure that the units in the exponent cancel out. It's like sines and cosines. You cannot have units in a sine or a cosine. You can't have units in exponents either. Now, the capacitor voltage is directly proportional to the charge because Q equals CV. So VC equals V naught times the exponent minus T over tau, or V naught is potential in the capacitor time T equals 0. The current can also be found to decay exponentially by taking the derivative, dq dt, and then I will end up being Q naught over tau times the exponent minus t over tau, or Q naught over RC times the exponent minus t over tau, or V naught over R times the exponent minus t over tau, or I naught times the exponent minus t over tau. There's a million different ways you can write that. Okay, so here, of course, this is sort of a recap. For the Physics 222 students, the calculus-based physics students is a recap, so to put it all on one slide. If you are a non-calculus physics student, an algebra-based physics student, this is where you should be starting. Okay, so the capacitor capacitance C is fully charged to charge Q naught and potential V naught, which of course is Q naught over C. To discharge it, you close the switch, the current starts to flow. The charge on the capacitor decreases according to Q equals Q naught times the exponent minus T over RC, in which Q naught is C V naught, and that's the initial capacitor charge. During discharging, the current and the voltage across the capacitance are I equals minus Q naught over RC times the exponent of minus T over RC, and VC equals Q over C, which equals V naught times the exponent of minus T over RC. When the switch is thrown, the capacitor briefly acts like a battery of potential V naught. The initial current is I at T equals 0, Q naught over RC, or Q naught over tau, or V naught over R. So in other words, it's limited by the resistance in the circuit. This is a decaying exponential, and at time t equals infinity, Q, VC, I, and VR are all at 0, and at that point, the capacitor acts like an open switch. This is a plot of the charge versus the time in terms of the time constant. Notice that it's a decaying exponential. Also notice that after one time constant, 1 tau, you're down to 37% of the initial charge. After 2 time constant, you're down to 13% of the initial charge. Now, later we'll have a slide showing this calculation. Here, of course, is the current in terms of the time, again in terms of time constants. After 1 time constant, you're down to 37% of the initial current. Both of these are decaying exponentials. So the notes on units, again, reminder on units. This is where people screw this up. 1 second is 1 farad ohm. The units and exponents must cancel out completely. then you can see, of course, seconds divided by seconds is going to cancel out. If it doesn't, you got a problem. Okay, now here is some investigation of what a time constant really means. So here are the equations, okay, and this is for discharging a capacitor. And as time passes, this acts like a decaying exponential, and at time t equals infinity, Q, I, VC, and VR all drop to zero. The capacitor then acts like an open switch. So after one time constant, we're looking at this exponential term in here. The exponent of minus RC over R is equal to the exponent of minus 1. It's just one time constant. If you put that on your calculator, and you should do that to practice, it ends up 0.368. So this means the charge at one time constant is 0.368 of what it was initially. That is 36.8% remaining charge. That is 63.2% discharge. You take 100% minus 36.8, you get this. You get 63.2%. After two time constants, the exponent minus 2, that's 0.135 or 13.5% remaining charge or 86.5% discharge. At the three time constant is the exponent of minus 3, and that is 4.98% charge or 95.0% discharge. At the four time constant, it's 1.83% remaining charge or 98.2% discharge. After five time constants, it is 0.674% charge and 99.3% discharge. So after five time constants, you're more than 99% of the way to the final equilibrium values. For most RC circuits, this much is much less than a second. Now, later we're going to compare this to slide 12 for charging. And you're going to notice these numbers here on slide 12 are the same as those over there. Okay, now which charge capacitor discharges more quickly after the switch is closed? Now, the only thing that determines how fast something discharges or charges is the time constant. So you want to look at the time constant. And the time constant is RC. And it turns out that the time constant of circuit A is 2 ohms times 6 times 10 to the minus 6 farads, or 12 microseconds. The time constant of B is 3 ohms times 5 times 10 to the minus 6 farads, and that's 15 microseconds. So circuit A discharges quicker. We did the discharge. Now we're going to charge the capacitor. Let's start with the capacitor initially uncharged. And this is for Physics 122 students, Physics 220 students, both algebra and calculus-based physics. The capacitor of capacitance C is initially uncharged. To charge it, we connect it to a battery. We're going to assume it's ideal of EMF E and close the switch. By writing the loop rule and applying differential equations, it is discovered that the charge on the capacitor increases according to Q equals C times E times the quantity 1 minus the exponent minus T over RC, in which the final value is C times E, and that's, of course, the maximum value. That's the equilibrium or final charge, and the time constant, of course, is still tau equals RC. By applying calculus, it's found that during the charging, the current and voltage are I equals E over R times the exponent minus T over RC. And VC equals Q over C, which equals E times the quantity 1 minus the exponent minus T over RC. As the capacitor builds up charge, its potential increases as a function of an exponential, and the current exponentially decays to zero. So here's how it charges up, here's how it decays. And notice this is a decaying exponential. This is sort of like the inverse of a decaying exponential. It's a decaying exponential flip. So charge increases according to Q equals CE times the quantity 1 minus the exponent minus T over RC. The time constant is tau equals RC. The current and voltage are I equals time rate of charge, and that equals E over R times the exponent minus T over RC, and VC equals Q over C times E times the quantity 1 minus the exponent minus T over RC. Now, at time t equals 0, we're going to look at the extremes here. At times t equals 0, I naught is E over R. The current is limited by R because the capacitor acts like a wire without resistance. In other words, it acts like a short circuit. Charge, of course, is 0 because it hasn't had time to build up yet. And, of course, the voltage across capacitance is also 0 because the charge is 0. And the voltage across the resistor is the EMF of the battery. At times t equal infinity, that's after a very long time. The current is 0 because the capacitor is fully charged and acts like an infinite resistance, in other words, an open circuit. Q infinity is C times E, and of course that's the maximum charge you're going to get. And VC, of course, equals E, and VR is 0 because the current is 0. So now we're going to look at the time behavior of charging a capacitor in terms of time constants. 1 time constant, 2 time constants, etc. The formula is Q equals C times E times the quantity 1 minus the exponent minus T over RC. Of course, tau is still RC, and the VC is still Q over C. And as you charge the capacitor, both Q and VC build up until Q infinity is CE, and VC equals E, while I and VR approach zero at time t equals infinity. After one time constant, we can use the formula 1 minus the exponent of minus RC over RC, or 1 minus the exponent of minus 1, and that's 0.632. Now, if that looks familiar, it should be. Remember slide 8? After two time constants, you plug it in, it's 1 minus the exponent of minus 2, it's 0.865. So now we're going to do that for these various time constants. One time constant is 0.632. So that means after one time constant, the charge is 0.632 of what it's going to be. So it's 63.2% charged. So you're 63.2% of the way there. After two time constant is 1 minus the exponent of minus 2, which is 0.865. You're 86.5% of the way charged. After three time constants, 1 minus exponent of minus 3 is 0.950, or 95.0% of the way to where you're going to full charge. After four time constants, 0.982, or 98.2% of the way fully charged. After five time constants, you are 99.3% of the way fully charged. So after five time constants, again, you're more than 99% of the way to the final equilibrium values. For most RC circuits, this is much less than a second. The numbers here on slide number 12 are the same as these numbers on slide number 7. Okay, and they indicate how far you've come toward your final goal. In other words, these are how far you've gotten toward being completely discharged, and these are how far you've gotten toward being completely charged. And that's the power of time constant. Okay, the capacitor is initially uncharged. Immediately after the switch closes, the capacitor voltage is. Well, it's going to be zero because the voltage increases with time, because it builds up as the capacitor charges. Which uncharged capacitor charges more quickly after the switch is closed? Hint, check the time constant. Capacitor A with a capacitance of 6 microfarads, a resistance of 2 ohms. Capacitor B with a capacitance of 5 microfarads and a resistance of 3 ohms. Well, time constant is RC. So we compare the two. Tau A is 2 ohms times 6 times 10 to the minus 6 microfarads, or 12 microseconds. Capacitor B is 3 ohms times 5 times 10 to the minus 6 farads. That is 15 microseconds. So capacitor A will charge more quickly. Which initially uncharged capacitor has a greater final charge a long time after the switch is closed? Assume the ideal batteries are identical. A hint, Q equals CE. Well, capacitor A has a greater capacitance, so it's going to have a greater magnitude of charge at the end. And it also reaches the final charge more quickly than capacitor B because its time constant is shorter than that of B. The red curve, that's this one, is marked with a fat arrow, shows how the capacitor in an RC circuit charges after the switch is closed at time t equals 0. Now, the reason I marked it with a fat arrow is sometimes the color doesn't come out very well on these slides, especially when you convert them to PDF. So this one is the curve I'm talking about. And which curve shows the capacitor charging if only the value of the resistance in the RC circuit is reduced? Reduce the resistance, the time constant gets reduced. That means the capacitor will reach its final charge more quickly. It's not going to have more charge. It's going to reach its charge more quickly. Okay, so Q equals CE. Q has not changed, but tau equals RC, so reducing R reduces tau. So we look for the curve that reaches the same ultimate value of Q, which is right here, but in a shorter time, and that is curve B. Curve B has a smaller time constant, same ultimate amount of charge. Now, I mentioned before the tires are made to be conductors, especially modern tires. And this is part of the reason why. Because charge builds up on a car battery. You've probably noticed this on cold days when you get out of a car or you get into a car and you touch the side of the car on a cold, dry, windy day and you get that shock. That can be dangerous at a fuel stop. Now, it's especially dangerous for race cars because they don't want to wait any amount of time for that charge to bleed off. So as the car rolls along pavement, electrons move from the pavement first onto the tires and then onto the car body. And even the passing air can store charge on a car. The car will store this excess charge and the associated electric potential energy as if the car body were one plate of a parallel plate capacitor and the pavement were the other plate. When the car stops, it discharges its excess charge and energy through the tires, just as the capacitor can discharge through a resistor. If a conducting object comes within a few centimeters of the car before the car is discharged, the remaining energy can suddenly be transferred as a spark between the car and the object. This is potentially very bad news if the conducting object is a fuel dispenser. The spark might ignite the fuel vapor and cause a fire if the air-fuel mixtures within the ignition stoichiometric mixture, and the spark energy is more than a certain critical value, which is U fire or 50 millijoules. Now, the spark will not ignite the fuel and cause a fire if the spark energy is less than the critical value of 50 millijoules. When the car stops at time t equals 0, the car ground potential difference is V naught equals 30 kilovolts. By contrast, dry air has a dielectric strength of 20 kilovolts per inch, which means you'll definitely get a spark. It'll be about 1.5 inches long. The car ground capacitance is 500 picofarads, and the resistance of each tire is R tire equals 100 gigaohms. The tires are actually made to conduct electricity. The carbon that makes them black and the steel belts can conduct and drain off charge. How much time does the car take for the energy to drop below the critical value fire? Now, I remember when I was a child, tires in those days were not steel belt radials, and people actually attached chains under their car that would drag along the pavement and hopefully short out the capacitor plates between the car body and the ground and allow the charge to discharge more quickly. Okay, so U fire is, of course, 50 millijoules. You write down the knowns and unknowns. U fire is 50 millijoules. Convert everything to SI, so 50 times 10 to the minus 3 joules. V naught is 30 times 10 to the third volts. C is 500 times 10 to the minus 12 farads. Resistance of the tires, R tire, is 100 times 10 to the ninth ohms. There are 4 tires, which is a good thing because they're connected in parallel. We need to know how much time it takes for U to get less than that critical value, for the energy to drain down to something less than the critical value. We're going to model the tires as 4 parallel resistors, and the car is one plate of a parallel plate capacitor. The other plate is the pavement. Now, the good thing about this is these resistors are connected in parallel, so the resistance is going to be 1/4 of one of them. The equivalent RC circuit is C and R. They're connected in parallel, so 1 over R equivalent is the sum of 1 over RJ. U equals Q squared over 2C, that's just the energy on the capacitance. Q equals Q naught times the X1 minus T over RC for a discharging capacitor, and Q equals CV. So now we can start doing algebra. We find out, because they're all similar tires, they all have the same resistance. The effective resistance, or the equivalent resistance, is R tire divided by N tire. Of course, there are 4 tires, so it'll be R tire divided by 4. U is Q squared over 2C. We can start plugging in for various things. And we do that, do a little bit of algebra here. We find out that U equals V naught squared over 2 times the X1 minus 2T over RC. And we can then solve that. X1 minus 2T over RC equals 2U over CV naught squared. Now go and take the natural log on both sides of the equation on the previous page and do a little bit more moving things around. And we find out that T is going to be greater than minus R tire times C over 2N tire times the natural log of this quantity, 2U fire over C V naught squared. Now we can start plugging numbers in. Okay, so T is greater than minus 100 times 10 to the ninth ohms, that is resistance of a tire, times the capacitance, which is 500 times 10 to the minus 12 farads, divided by 2 times 4 tires, times the natural log of this entire quantity here. 2 times 50 times 10 to the minus 3 joules for U fire, divided by the capacitance of 500 times 10 to the minus 12 farads, also divided by the square of the V naught, which is 30 times 10 to the third volts. So this time is greater than 9.4 seconds for a 100 gigaohm tire. Now this is unacceptable. No pit crew is going to wait 10 seconds to start refueling the car. So what we want to do is lower the resistance of tires by a factor of 10. If we do that, we get time, the T, down to less than about a second, which is much better. Now, the tip to this is be very careful when fueling, especially in winter when humidity, which helps drain off the charge, is low. That's when you're most likely to get a spark. And if you do get a fire, don't take the nozzle out of the tank. If the nozzle's out of the tank, stick it back in because you're going to cut off the vapor. If the vapor is not the right air-fuel mixture, it won't ignite and it won't explode. The vapor in the tank doesn't explode and it doesn't ignite. It's the vapor that's mixed with the air around the nozzle that explodes. So if you put that nozzle back in the tank, it'll put out the fire. The worst you can do is panic and dance around with it. A 10 kilo ohm resistance is connected in series with a capacitor and a battery VMF 36 volts. If the time constant is measured to be 15 microseconds, calculate the total capacitance and the time it takes for the voltage across the resistor to reach 20 volts. You write down the knowns and unknowns. Tau equals RC, or 15 times 10 to the minus 6 seconds. The EMF of the battery is 36 volts. The resistance is 10 to the 4th ohms. The voltage across the resistor is 20 volts. We need to know the capacitance and the time. The physics of this is an RC circuit with a charging capacitor, time constant, and a loop rule. The formula is tau equals RC. We know that minus VR minus VC plus the EMF of the battery equals 0. That's just going around the circuit. Okay, so it's VC equals the EMF times the quantity 1 minus the X1 minus T over RC. We can rearrange this and solve. The capacitance C equals the time constant over R. So that's 1.5 times 10 to the minus 5 seconds times the units conversion divided by 10 to the 4th ohms. It is 1.5 nanofarads. Rearrange and solve for VR. VR equals VC minus the EMF, or the EMF times the quantity 1 minus the exponent minus T over RC minus the EMF, and that equals EMF times the exponent minus T over RC. We can divide by VR, rearrange, take the natural logs of both sides, and when you do that and solve for T, so T equals RC times the natural log of the quantity EMF divided by VR. So this is 1.5 times 10 to the minus 5 seconds, because that's RC, that's the time constant, times the natural log of the quantity 36 volts divided by 20 volts. The volts cancel out, as they must. If they don't cancel out, this won't work. Okay, so it ends up being 8.8 microseconds. A series RC circuit has a resistance of 5 kiloohms and a capacitance of 6 microfarads and a 100-volt DC power supply. The capacitor is fully discharged at the beginning. How long does it take for the charge to rise to 95% of its final value? Okay, the knowns and unknowns. The resistance is 5 times 10 to the 3rd ohms. The capacitance is 6 times 10 to the minus 6 farads. The final charge, Q, is 95% of the way there, so that's 0.95 times QF. V naught is 100 volts, and we need to find out time. The physics of this is an RC circuit with a charging capacitor. Tau equals RC, Q equals 0.95 QF, and Q equals Q naught times the quantity 1 minus the exponent minus T over RC. We can solve for Q, so Q equals 0.95 Q naught, or Q naught times 1 minus the exponent minus T over RC. So then that means that the exponent minus T over RC has to equal 1 minus 0.95, or 0.05. So T equals RC times minus the natural log of 0.05. So RC, of course, is 5 times 10 to the 3rd ohms times 6 times 10 to the minus 6 farads times the negative of the natural log of 0.05. We probably could have reduced this a little more, but I didn't bother. It ends up being 0.090 seconds. Now, there's a much easier method. So 95% of the final value corresponds to 3 time constants. So T equals 3 tau, which is 3 RC, which is 3 times 5 times 10 to the 3rd ohms, times 6 times 10 to the minus 6 farads. That ends up coming out 0.090 seconds. What effect, if any, does increasing the battery EMF in an RC circuit have on the time to charge the capacitor? Well, the time to charge the capacitor depends only on the capacitance and the resistance. It does not depend on the battery EMF. The resistance in an RC circuit is comprised of a 1.5 megohm resistor in parallel with a 2 megohm resistor. What is the time constant for this circuit? The capacitance is 2.5 microfarads. Well, the resistors are 2 of them connected in parallel, so we can do product over sum. So we do R1, R2 divided by the quantity R1 plus R2. So 1.5 megohms times 2 megohms divided by the quantity 1.5 plus 2 megohms ends up being 0.857 megohms. Then RC is 0.857 times 10 to the 6 ohms times 2.5 times 10 to the minus 6 farads, or 2.1 seconds. In the physics lab, Rebecca measures the voltage across an unknown capacitance RC circuit every 10 seconds after the switch in the circuit that allows the capacitor to discharge is closed. If the switch is thrown at time t equals 10 seconds, and the capacitor is initially fully charged, using the graph, estimate the time constant. So here is the 10 seconds where the switch is closed. Hint, at one time constant, V equals e to the minus 1 V naught, or 0.368 V naught. So what you want to do is you want to look at the graph and figure out what V naught is, which is about 6.4, takes 0.368 times that, and then look at graph again to find out where it intersects the graph and what is the time. Okay, so from the graph, V naught is 6.4 volts. At t equals 1 time constant, V equals the exponent of minus 1 V naught, or 0.368 V naught. So V equals 0.368 times 6.4 volts, which is 2.35 volts. If you look at the graph, that's right about here. And then you intersect and drop down. It ends up to be about 17 seconds, which is 7 seconds. Remember that took 10 seconds before the first reading took place? It's 7 seconds after the switch is thrown. An RC circuit contains a battery, a switch, a resistor, and a capacitor, all connected in series. Initially, the switch is open, the capacitor is uncharged. Which one of the following statements correctly describes the current in the circuit during the time the capacitor is charging? Well, the current is always a decaying exponential, so it decreases. So I equals E over R times the exponent minus T over RC. So it's a decaying exponential. An uncharged 5 microfarad capacitor and resistor are connected in series to a 12-volt battery and an open switch to form a simple RC circuit. The switch is closed at T equals 0 seconds. The time constant of the circuit is 4 seconds. What is the charge on the capacitor after one time constant has elapsed? It's 3.8 times 10 to the minus fifth coulombs. After a time of one time constant, Q equals the exponent of minus 1 times QF, which is 0.637 QF. So Q will be 0.637 times C times V is 0.637 times 5 times 10 to the minus 6 farads times 12 volts, or 3.8 times 10 to the minus fifth coulombs. An uncharged 5 microfarad capacitor and resistor are connected in series to a 12-volt battery and open switch to form a simple RC circuit. The switch is closed at time t equals 0 seconds. The time constant in the circuit is 4 seconds. What is the charge on the capacitor after 3 time constants have elapsed? It is 5.7 times 10 to the minus fifth coulombs. After 3 time constants, Q equals the exponent of minus 3 times QF, or 0.950 QF. So Q equals 0.950 C times V, which is 0.950 times 5 times 10 to the minus 6 farads times 12 volts, or 5.7 times 10 to the minus fifth coulombs. Thank you.